Now I'm about to tell you a classical computer science problem involving finding the shortest path between two vertices. If you already know the algorithm, I want to challenge you to prove it to yourself, instead of just jumping at coding up the solution. Along the fields of Nerf firms is a cow named Beef, for no particular reason, and Beef's bestie is Cheese, who lives in a field far away from Beef. For Cheese's birthday, Beef decides to go surprise her at her field. Each field in Nerf firms has at least one road connecting it to another field, and each road costs a certain amount of money to cross. Noting that cows don't make a lot of money, since they are more like prisoners than employees, Beef wants to figure out the cheapest route to get to Cheese. Your job is to figure out the minimum cost that Beef will incur in order to get to Cheese, keeping in mind that Beef can be up to 100,000 fields away from Cheese. This problem is an example of a single source shortest paths problem, which is a problem which involves queries to find the shortest path from a starting vertex to some arbitrary vertex in the graph. These types of problems are really iconic because Dijkstra's algorithm can be directly applied to it. For those who haven't heard of it before, here is a speed run explanation for the basics of Dijkstra's algorithm. Dijkstra's algorithm is a pathfinding algorithm which really chooses the route with the smallest cost. For each vertex, we calculate the shortest path to it from the starting vertex and use it to calculate vertices which are adjacent to it. Now, you might be like, that sounds all dandy and all, but if n is up to 100,000, how can we possibly make it one in time? To figure out why this will one in time, we need to analyze the nature of Dijkstra's, or rather that it generates in a way where, I'll call it d, where d to the I equals the minimum distance from Beef to I, or our starting vertex to I. And then, now that we have this formula, we can actually make a couple of optimizations. Or, like here. Let's say that we have an example graph where Beef is currently at this field and Cheese is currently at this field. Then, if we want to calculate d of Cheese, which I'll abbreviate to c, then what would it be equal? So if we want to do this a very straightforward brute force way, we could start a lot of searches from Beef and then just go through every possible route to get to Cheese. But do we really have to do that? Or every search, it will have in common going through either this node or this node, because to get to Cheese, we have to either go through this field or this field because they are the only fields which have a road to Cheese. And then by definition, I'll call these JK. If d to the j is the minimum to get to j, and d to the k is the minimum to get to k, then we can actually rewrite d to c as the minimum from dj. And you have to take it on this word because this isn't counted yet. So I'll call this cost. And from j to c are basically the same thing with k. Now, this formula is only dependent on the adjacent nodes, so we really only have to consider each node once. So if n is the number of nodes, and m is the number of edges, then right now we are looking at an O of n one time. But that's actually not true, because what if we visit this node before we visit j or k? Then that won't work out. So we have to traverse them in a specific order. And to remedy this problem, we can actually keep going to the node which is closest to Beef. So if we want to do that, then we could store like a priority queue, or essentially a data structure which always keeps the minimum element in front. This will add an m log n factor to our time complexity. So now our time complexity of this algorithm is going to be O of n plus m log n, which is sufficient for n up to 100,000 or 10 to the 5th. Okay, so it seems like it one's in time, but we're still not sure whether making locally optimal moves will always guarantee a globally optimal solution in this case. And so let's try to see a more concentrated proof. Okay, let's start off with an algorithm that we know will work. So let's say that we have like a dummy cow, right? And just have like a lot of dummy cows. And then these dummy cows are essentially going to just do our traveling for us. So we have one going to here, and then we have one going to here. Then this first one goes here first, and then this is marked down. And then a quality that I can do using this example is that we know that this algorithm is going to guarantee us the shortest path because we're trying all possible routes. But it's pretty intuitive to realize that if an ant gets to a node already, it's never optimal for another dummy cow to get there later on because the time will just be longer. So you can set minimum distance here to 8. And then note how simultaneously we also have to start dummy cows going elsewhere. So we have one going out this way, we have one going out this way, and then we have one going out this way. So next in line is this one. So this dummy cow will get to node 2 next. So we're going to color this in because we're no longer going to go to it anymore, and this will become 21. Great. And now next in line comes this dummy cow, and then it'll reach node 4 in 8 plus 23, which is 31. This in turn will also essentially get rid of this cow's need to go at all because we've already went there, so you can just get rid of it. And then next we have this cow, which is going here, so that will be a 45 plus 8, which is a 53. Or also there's another cow going here, but it's not really needed because 31 plus 25 is greater. So this one is over, and then there's one more cow going this way, but this cow gets here first, so a minimum distance is 53. And now because of this, note how our basic all routes algorithm is basically doing the exact same thing as our Dijkstra's algorithm, just getting rid of any paths which will always be a shortcoming. And then the reason why our locally optimal decisions can essentially affect our globally optimal decisions is because our way of processing nodes is by time to get there. So we're going to process all nodes before we process any nodes with longer wait times. So if anything ever cuts it off first, then that'll be it. And so just like that, we have intuitively proved Dijkstra's algorithm in less than 5 minutes.